All right, we are looking at section 6.5, which is trapezoidal rule, and we will also be talking about Simpson's rule. So let's take a look at the first. Okay, trapezoidal rule basically is finding the area under a curve when you want to use trapezoids instead of rectangles, like we've done in the past with Riemann sums. So let's take a look at this function, which we're interested in the area under the curve from -1 to 1. And we're going to go ahead and break it up into 4 equal subdivisions. So I intend these to be equal. If they're not exactly, just bear with me, and we will believe that they are equal. And I'm going to go ahead and make the trapezoids so we can see them. There is 1, 2, 3, and the easiest one to see is there, 4. So we have 4 trapezoids, and basically the trapezoidal rule says find the area of all the trapezoids. So I have 1, 2, 3, and 4 trapezoids. And I'm going to label our subdivisions so that we get a nice formula that you'll be used to seeing. We're going to go from A to B. Instead of -1 to 1, we'll just call it A to B. And I'll call this first subdivision A sub 1. And here at 0, we will call that A sub 2. And then here we will have A sub 3. And then we have B. So we want to find the areas of these 4 trapezoids. So let's begin with the first one. So we will have 1/2 B1 plus B2. Well, B1 is going to be the height of my function, which I will call f of x. I'll label that down here. Okay. And so the height at x equals a will be f of a. Plus the height at a sub 1 would be f of a1. And then we have to multiply it by the height of the trapezoid. The height of the trapezoid, these vertical lines end up being our bases, so the height is the width of the subdivision. And if we have a consistent width for all of our subdivisions, we can find that width by doing b minus a over the number of subdivisions. And that will be the height of each of our trapezoids. So height equals b minus a over n. And in our case, n is 4. So b minus a over n, so that's what we have to use for our height in our trapezoid here. And I'll go ahead and use b minus a over 4. Okay, so what I have now is the area of each of the 4 trapezoids. And that's all trapezoidal rule is find the area of the trapezoids and add them up. So you will often see trapezoidal rule written in a particular form. And let's go ahead and simplify this a little bit to show that form. So we can factor out a 1/2 out of each of our terms, and we can factor out a b minus a over 4 out of each of our terms. So I'm going to do that now. Okay, so what we have now is the 1/2 and the b minus a over 4 pulled out in front. And when we factor those out, what are we left with? We're left with an f of a coming from our first trapezoid plus 2 f of a sub 1, because we end up using f of a sub 1 in our first trapezoid and in our second trapezoid. So all of the vertical lines in the middle of our interval from a to b get used twice. So that's why we have f of a plus 2 times f of a sub 1 plus 2 times f of a sub 2 plus 2 times f of a sub 3, and then we finally get to the right end of our interval, and there's only one time that we use f of b. So this is what we would call the trapezoidal rule. Now, one thing that I want to ask about is, looking at this, we need to think about when the trapezoidal rule would overestimate or underestimate the area under the curve. And if you will notice, excuse me, that when our function is concave down, our trapezoid ends up being beneath the function, giving us an underestimate. When our function is concave up, our trapezoid ends up going outside the function, giving us an overestimate. So on this slide, we have a summary of the trapezoidal rule, which is what we have here. And we also have another way to do a trapezoidal approximation, which is just averaging a left Riemann sum and a right Riemann sum. That becomes handy from time to time, but I would say generally this form of the trapezoidal rule is used most often. I do have a note for you. Be careful. If the intervals are not a consistent width, then you must find the area of each trapezoid individually. We can't just plug into trapezoidal rule if the height of each trapezoid is not going to be the same. All right, next we have an example of finding a trapezoidal approximation with n equals 4 subintervals, and we are finding the area under the curve of x squared from x equals 1 to x equals 2. The first thing I suggest when you do a trapezoidal approximation or a Riemann sum is to sketch your function so you know what you're dealing with. So I will do that now. Okay, so I have a rough sketch of f of x equals x squared, and we are interested in the area under the curve from 1 to 2, and we have 4 subintervals. So what I have presented here is t equals our trapezoidal approximation, 1/2 times the b minus a over n, and then we have f of a plus 2 times f of a sub 1, and so on over to f of b, giving us 2.344. The next thing I wanted you to do on this problem is use your calculator to do the definite integral from 1 to 2 of x squared dx. And when we do that on the calculator, we get 2.333. And then finally, I want an exact value, which means I want you to use fundamental theorem of calculus to perform the definite integral. And we're doing the integral from 1 to 2 of x squared dx. We take the antiderivative and we get x cubed over 3 to be evaluated from 1 to 2. We plug in 2 first, so we have 2 cubed over 3 minus 1 cubed over 3, giving us 7/3. So the exact answer is 7/3, but our trapezoidal approximation gave us 2.344. The reason that they are not the same is that the function is concave up, so our trapezoidal approximation is going to overestimate a little bit. And we could have gotten a better approximation with the trapezoidal approximation if we had used many more trapezoids. The more trapezoids you have, the closer you will be to the exact value. All right, our next topic is Simpson's rule. Simpson's rule is another way to approximate the area under a curve, but Simpson's rule is based on parabolas instead of trapezoids or rectangles. And Simpson's rule is an AP topic. I do want you to be familiar with it. You are responsible for knowing it. But we are not going to derive the entire Simpson's rule. What you will be doing on your own is Exploration 1 on page 313 in your book, which goes through a derivation to show where the basis of Simpson's rule comes from. So things to remember about Simpson's rule: when we talk about h in the equation, it is still b minus a over n. And our intervals are partitioned into an even number, n subintervals. And when we do that, we still have a coefficient of 1 for the left side, 1 y sub 0, and a coefficient of 1 for the right side of our interval, y sub n. And then it alternates with 4s and 2s within on the interior vertical partitions. So we end up with this h over 3 times the quantity y sub 0 plus 4y sub 1 plus 2y sub 2 and so on up to y sub n. This gives us another way to approximate area under the curve, and it could be very useful when we have a very curvy function, because parabolas would probably approximate the area under the curve more accurately than rectangles or trapezoids.